All right, so I'm starting the partial fraction technique. This is the second technique that we're gonna focus on for integration techniques, and there's quite a bit involved with this technique, but as long as you understand the systems of equations from grade 11, as well as solving the rational expression stuff out of grade 11, it's pretty straightforward. Okay, so there's quite a bit involved, and I'm going to do it over 3 videos because there's 3 main types that we're going to focus on here. And so I'm going to do, the first video will be the first type, obviously, and then so on and so forth. And then there's other types, but as you see here at the end here, I've got 4 and 5. Well, 4 and 5 are just so similar to type 3 and a mix of 1 and 2 that once a person sees them next year or whatever, you won't even think of them as any different. They're more or less the same stuff. So here it goes. So if the degree of the denominator, so the bottom of the fraction, is greater than the numerator, and you're trying to do integration. Now, of course, we always want to try substitution, but that's when we would use partial fractions if you can't simplify or if it doesn't work with substitution and stuff like that. Okay, so again, if the bottom degree is higher than the top degree, so it doesn't matter if it's 1 degree higher, 2 degree higher, 3 degree higher, just that's when you've got to think about partial fractions. But you have to do substitution technique first. Okay, if you got that under control, then you're good to go. So here we go. The examples are quite long, so you'll see that I'll have to stretch them out over two pages at least here. So here's our first example. Now I'm looking at this, and right off the hop, I think of the substitution on the bottom is derivative would be 2x plus 1. Doesn't substitute out the x plus 5. So this is a perfect example of partial fractions. Now you'll notice I got it written as type 1 linear factors that are non-repeating. Now I know that looking at it because of course I want to factor this out. I'm going to try to write a bit smaller and use up as much of this page as possible. So you'll want to factor everything that you can. So I got x plus 2, x minus 1 dx. So in the bottom, you can see that we've got non-repeating linear factors. And again, linear is like y equals mx plus b, right? There's no exponents and stuff like that. So here it is. So now how we do this is we split this guy up. Now this is just a technique. This is something that you have to kind of either memorize or remember how to do. But once you do it, it's pretty straightforward. So in non-repeating linear factors, this is how you set it up. You're going to set it up as an integral of x plus 5 over x plus 2, x minus 1, and you're going to set that equal to 2 separate fractions, or 3 if there was 3 non-repeating linear factors, or 4 or 5, whatever it is. But this is how you do. You go like this. Here, maybe I'll change the color on this side so you can see. So I'm splitting this up as integrals, and I'm going to go a over x plus 2, because that's our first linear factor, plus the integral b x minus 1. So there's our 2 things. What we're trying to find is we're trying to find an a and a b that'll equate to the x plus 5, so that we can do it as 2 separate integrals, just like in substitution when we had to break up integrals into the sum of a bunch of integrals. That's essentially what we're trying to do, but we need to figure out what a and b are so that this would work. So kind of trying to figure out what fraction would equal this whole big thing over here. So I'm going to get rid of that. So now what we do is or how I think of it is, we multiply the whole thing by the common denominator of x plus 2, x minus 1. Now remember, we're just trying to find a and b. So like, I kind of even ignore the integrals and the d of x and everything like that. So when I multiply this in, over on this side here, I get x plus 5 equals a, the x plus 2 cancels, so I'm left with a times x minus 1 plus b times x plus 2. So just like in grade 11 when we were solving rational equations, we were solving for x and stuff like that, that's kind of what we do. So now I'm going to take this onto the next page. I'm going to flip back and forth a couple times. All right, so this is where we left off. So now what we do is we start to equate everything. So I'm going to, or simplify everything. So I'm going to multiply this a in here, this b in here. So I get x plus 5, which is equal to ax minus a plus bx plus 2b. Now, again, that being said, remember, when we look back, we're saying that this side equals this side. So again, when I go back over here now, this is where I'm going to start to equate things. So I'm going to take each individual term. I'm going to take just my x terms, because obviously my x terms on the left-hand side equal my x terms on the right-hand side. Otherwise, there would be no equal sign, right? And then I'll call it my coefficient, my numerical coefficient on this side, the constant, equals the constant terms on this side. So we're going to write this out as kind of separate equations. So I've got x equals ax plus bx, and I've got 5, I'll write this one, 5 equals negative a plus 2b. Now the nice part is we can really just ignore the actual variable in this section. So I'm just going to look at the coefficient. So I'm going to change this to 1x, right? Just the coefficient. So 1 equals, the coefficient of this one is a, and the coefficient of this one is b. Like so. So now you can see we've got an equation here. We've got an equation here. Now I'm going to say something that goes back to grade 11 or even grade 10 systems unit, for instance, that if we've got two unknowns, which we do, a and b, and two equations, we can solve this. It's basically impossible not to be able to solve this unless there was no solution. If we had 3 unknowns, we'd need 3 equations. If we had 4 unknowns, we'd need 4 equations, and so on. So in this situation, all you're doing is a systems of equations, and I don't really care. You can go like this and say, put a star here and put in your notes, set up systems of equations. Set up systems, or solve systems. It doesn't really matter. I'm just going to get right to it here and say, let's say a equals 1 minus b. So that's what I'm going to do here. I'm going to use substitution method. You could do the elimination method. That would work fine as well. But I'm going to do substitution method because that's what I feel like doing right now. So I'm going to take this expression and I'm going to substitute it way over here into a in this one. So 5 equals negative 1 minus b plus 2b. And I simplify all that out. I get 5 equals negative 1 plus b plus 2b is plus 3b. Add the 1 over, I get 6 equals 3b. So b equals 2. So now if b equals 2, which is wonderful, I can substitute that back into an original, but in this case I'm just going to put it right there because I trust us. We get a equals 1 minus 2 is negative 1. So there's what we find for a and b. Okay? So I like that at all, but I'm going to have to take it over to the next page to show you now what we do with this, because remember, a is going to go here, b is going to go here, and we're going to do these integrals, and it's just like the previous assignment that you've done multiple times here. Okay, so I'm going to see right here we had A equaled -1 and B equaled 2. So I flip back and I'm going to write this whole expression down again, and we'll do the integral of it. Okay, so now I'm going to substitute the -1 in. So when I do this, I get the integral of -1 over x plus 2 dx plus the integral of 2 over x minus 1. And of course, we could use substitution method on this, but we're going to just kind of fast track this because you guys have done the substitution method enough now. I would hope that you'll realize that if you've got, here, let's put a big fat star here in red. That way we don't have to waste much time on it. Is if you have a constant over a linear factor. Constant over a linear factor. The integral is ln of the factor. I'm just going to put the factor in here. And of course divided by the a value, because that comes out too, and you'll see that later. And I'm talking a is the leading coefficient of that linear factor. In this case, they're both 1, so it doesn't matter. So when I want to do this, I see that I've got a constant over top of a linear factor, so it's going to be negative ln of x plus 2, just like so. Remember the absolute value part, plus another constant over a linear factor, 2 ln of x minus 1. And this all comes again, if you wanted to, you could do substitution method on each of these and see that this would work. But I'm just trying to show you that it would work out anyway, so we're just going to kind of fast track it. And then we're done, except we got to remember to go plus a constant. So there is what I would say is a pretty straightforward example of partial fractions, even though it's quite involved. You're going to find that these questions take half a page to a page in some cases, okay? So in the next example we do, this guy, hopefully you see that it's going to be, or it makes more sense to you, and we'll just deal with the coefficient stuff. All right, so first things first, I'm going to go factor everything just so that it simplifies. I'm not going to worry about the top so much. Okay, so I'm gonna do this a little bit faster so that it just gets done here, and you'll see. So I factor GCF out of the bottom, I get x, and then I get a trinomial difficult of 2x squared plus 3x minus 2. I factor that out, I get x plus 2, 2x minus 1, and now I can see that it's a type 1 again with non-repeating linear factors in the bottom. There's nothing repeating there, okay? So that's nice. So now I can set up a partial fraction method, of course, equals. I'll go like this. I know it's a over the first non-repeating term plus, now I'm just going to, like I said, go about this. There's nothing complicated about this part. Plus c over, 2x minus 1. So there's what our three integrals that we're going to do in the end of this question look like. So again, multiply everything by the common denominators, which is always these three, once you have it factored. So when I do that, x plus 2, 2x minus 1, I end up with x squared. I'm going to drop those integral signs for the time being because it doesn't really matter, equals a times x plus 2, 2x minus 1, plus bx, 2x minus 1, because the x plus 2 cancels, plus cx, x plus 2. Okay, cx, and then an x plus 2. Now, I'm going to go and I'm going to multiply all this out. I'm just going to pause the video here and do this so that it's just there, and then we'll set our coefficients of each term equal to each other. All right, so here's what all that simplifies out to. So now I'm going to just worry about the coefficients of my x squareds, my x's, and then my constant. So I got to find the coefficient of that's a 1, coefficient of my x is a 2, and my constant is -1. And I'm going to equate that to all the coefficients on this side over here. Okay. So here's how I'm going to set this one up so we can kind of see it a little bit better. Again, I'm only worried about the coefficients of each. So back to here, my x squared term right there is a 1. So I'm going to say 1 equals, on the right hand side I've got, for the x squareds, I've got a 2a plus 2b plus c. So 2a plus 2b plus 2b plus 2b minus or plus c. So there's our x squared coefficients for our x's, so 2a plus 2b plus c. For our x coefficients, I got a 2 on the left-hand side. I've got a 3a minus b plus 2c. So again, we've got 2 equals 3a minus b plus 2c. So if you're writing the notes out for this, you'll see that it should all fit on your page coming down. And now for the constant factor, we got a -1 on the left-hand side is equal to a -2a. Well, that one's fairly simple. So -1 equals -2a. Beautiful. Nice and easy. So obviously, we've got 3 unknowns. We've got 3 equations. Now we can start to solve. Now, you can do this again any number of ways. It's a matter of figuring out which one you want to solve for and substituting the other, or you could use determinants. You could do any of that stuff. But this one here makes it pretty easy for us to eliminate a whole equation. I can say a equals 1/2 from this guy. And now, when I go to simplify this, I'm going to come over here and I'm going to say, well, 1 equals 2 times 1/2 is 1 plus 2b plus c, and it's just busy work, you guys. So don't freak out about the busy work. It's just simplifying stuff and doing systems of equations. It's the techniques you have to do. You're not getting a whole bunch of these, so get used to it. So let's go and do this. I think what I'll do is simplify it, and then I'll set up maybe elimination method this time, show you that you can do elimination method. So I'm just going to simplify these for a second. Okay, so here's my 2 equations, and once I simplify them, okay, so on this middle equation, I obviously got rid of the fraction. I just times everything by a 2 and then got rid of the constant. So now when I do the elimination method, I'm going to bring this guy over. I get 0 equals 2b plus c. And I'm going to add these 2 equations. So I get 1 equals, my b's cancel out, and I get 5c. So c equals 1/5. So we've already got 2 of our variables. We've got a and we've got c. So now I can go get b pretty quick here. I'm going to plug it back in. I'll just plug it into this guy, I guess. And I get, using a little mental math here, we get b equals -1/10. Beautiful. So again, now we're going to take those 3 numbers back over into this guy. There's our equation that is equal to our question. So that's what we want to solve. So we're going to plug our 1/2, our -1/10, our 1/5 in there. And of course, those are constants, so I'll just bring them out front anyways to make it a little bit easier to look at. So we're going to have something that looks like this. Let's go with the integral. Well, that a was 1/2, so 1 over x. The -1/10 integral, so 1 over x plus 2, because that was what was under the b. we'll take the constant of 1/5 out, which is our c. And you could put these on top if you wanted to, but you're going to factor them out anyways, so it doesn't really matter. 1 over 2x minus 1. Oh, and we should have our dx's in there, but for what we're doing, I'm not too concerned about it. It's all about the process. So let's use that cheater method. You can go do substitution if you want again, but cheater method, we've got a constant over a linear function, we've got a constant over a linear function, we've got a constant over a linear function. So we know that it's going to be 1/2 ln of x minus 1/10 ln of x plus 2, and then plus 1/5 ln of 2x minus 1. Now, if you go back to that note that we wrote, we also have to remember to divide by our a value. So I'm going to divide this by 2. So my final answer is going to work out to 1/2 ln of x minus 1/10 ln of x plus 2 plus 1/10 ln of 2x minus 1. And again, you don't have to do it this way, but I mean, cheating and just going fast method, but I think most of you will, because after a while you get tired of doing the substitution method on these big long ones. So there's type 1, and you can see after 21 minutes or whatever it's been that it's busy work. That's really all it is. It's more or less grade 10 and 11 math for calculus. So try a couple of those type 1s, see if you can do some of them, and then I'll throw up video 2 and you can see the difference. It's not a whole bunch different. You'll see the little simple things that happen though.